Welcome and good morning, good afternoon, or good evening, depending on where you are. Thanks for coming out to my talk, Formalizing a Language. Today we're going to talk all about the Python language. It is, after all, a real language. We say it all the time, but I don't know how many of us stop to think about how much Python shares with natural languages. It is a written form of communication. We write it, we read it, sometimes we even speak it, like at conferences. It's composed of words, although in Python, some of the words will look like English words. Some of them are just numbers. Sometimes whole strings will contain what we consider multiple words as a single word to Python. And sometimes just a couple symbols together is a word to Python. But we still use these words to build up larger sentences, which in Python is usually called statements, just like in natural language. And we can keep going down with this analogy, where sentences form paragraphs, those paragraphs form essays, and we run these as programs. One of the guiding philosophies in designing Python is that code is read much more often than it is written. And this is true. So Python's put a lot of effort into making its code readable by humans. When one of us reads a line of Python, whether in our own heads or out loud, we parse it similar to a natural language. So we look at a statement such as this, and if I wanted to communicate this code to another developer, I would probably say the statement is as follows: up equals requests.get https status.python.org. Now, if I say that sentence out loud and another developer recreates this line exactly, which I think is entirely possible here, that was a good form of communication. But it was not sufficient for computers. If I wrote down exactly what I said, it would not be this line, and the computer would not know what to do. The computer would not know from my reading of this line that there was a method call, or that method was getting an argument of a string, or what was in that string, as I left out several of the symbols in my reading of it. So although we parse code as natural language, human to human, that doesn't really work for the computer. And although humans read code much more often than they write it, computers read code even more than humans do. Every time you're executing a program, the computer is reading the thing you wrote and having to parse it into something that actually makes sense to a computer, because it's not this line of text. So a computer will also parse this line, but instead of putting it in something like natural language, it's going to put it in a much more computer concept, a tree, specifically a syntax tree. So when Python thinks about what this code means, it's going to turn it into something like this. An abstract syntax tree that tells the computer not only what was in the statement, what are the individual words, which ones are significant, how do they relate to each other, which ones have precedence, which ones are lined up with each other. And this ultimately is how the computer is going to make sense of what we write. And so this whole process of going from text to code that can be implemented on your machine is compiling. So here we're compiling Python. And this is a multi-step process in order to fully transform the text into code. The first step in that process is lexing, which is also sometimes called tokenizing, because it's the act of turning just a stream of characters into tokens. It informs the computer where the word boundaries are. So if we ask Python's built-in module tokenize to make sense of this statement that we had earlier, it'll tell us some things about where it thinks different words are. You'll notice that some of the white space does not end up in any of the tokens because it's actually insignificant to Python, but it was nonetheless just fine figuring out where the word boundaries are, whether the word was surrounded by white space, as in up, or whether it was entirely enclosed by other tokens, such as get. However, you probably know that not all white space in Python is insignificant. There's quite a lot of significant white space. In particular, all statements in Python end in a new line. So the tokenizer actually added one to our statement, even though it was not in the original text. It had to do this because it would not be a complete statement unless it ended in a new line. After we have a stream of tokens, we can then take that and pass it to our parser. The parser is the engine that turns that stream of tokens into a syntax tree. So it makes sense. Instead of just having a list of names or words, Python is able to determine what you wanted the program to do and how it's going to eventually do that for you. Parsing involves following a set of grammar rules that ultimately give the structure that is the syntax tree. So if we ask the Python built-in module AST, which stands for Abstract Syntax Tree, to make sense of the earlier statement, it will spit out something pretty similar to this, which doesn't quite look like a tree at first unless you turn your head to the side, and you can kind of see that our root node assign is the outermost call object, and our leaf nodes of names are kind of the more indented objects. The final step before the computer can actually run your code is to turn that tree into something that's even more familiar to a computer, a series of ones and zeros. So this is the complete instruction set for our statement. So these are each of the bytecodes that the Python virtual machine will execute in order to fulfill our statement. We can get this output from the built-in dis module, which stands for disassembly. You'll notice that the order is rather mixed up from how we wrote our code as a human, sort of just writing down syntax. The first thing up for the computer is to load requests, which was kind of in the middle of our statement. And the last thing it does is stores the name up. Well, that was the first thing we wrote out. The way which we write out code isn't necessarily the way the computer really wants to execute it. So part of this process of compiling is reordering it in a way that it makes sense on a computer. Although it doesn't seem to have any relationship to how we wrote the code originally, if you go back to the tree, you'll see that the order of bytecode is pretty much a bottom-up walking of the AST. So that tree is very important to getting the final code out. And that's the end of compiling Python. It's not so long of a process, but for the rest of the talk, we're going to focus on grammar. Which grammar are the rules that tell the parser how to transform a stream of tokens into a tree, which is the thing that ultimately gives structure to your code. Specifically, formal grammar is a set of rules that define what words are valid for any language. So for the Python language, there is an exact set of rules that determine what is a legal Python program, and because it defines the complete set of legal Python programs, anything that doesn't fit that grammar is determined to be not a Python program. It's an error. Note that just because your program is grammatically correct does not mean that it's going to run or be free of bugs or not crash. It just means that it'll be possible to try and execute it on a machine. So if we go back to our original statement once again, we saw earlier that it is lexically valid. That is, if we pass this statement to the tokenizer, it will give us back tokens and no errors. And it's also syntactically valid, the next step in that process. If we pass those tokens to parser, the parser will give us a valid AST and will not throw any errors. But if we change the statement slightly, so it almost looks the same, if you look at it real quick maybe, this is still a lexically valid text. If you pass this to the Python tokenizer, it will tokenize it and give you all valid Python words. There'll be no errors. But it's not syntactically valid. If you pass that specific stream of tokens to the parser, it will try every combination of rules it can find and eventually find none that satisfy it. And so it will give you a syntax error. And you won't even be able to run this text as a program. So this is where we're focusing for the rest of this talk. This is the entire process of compiling Python, but we're just going to focus in the parsing, which is the transformation of tokens into that AST. The parser takes in tokens and a grammar, and then its output is an AST, or if it's not valid, then some errors. Python's grammar, which is a set of rules that define what it is written in a single file in its source tree, and it's composed of a parsing expression grammar, usually shortened to PEG. This is just a classification of grammars of a grammar type that Python uses out of many theoretical possible types of grammar. And the parser, the thing that implements the grammar for it, is a packrat parser, which is just an efficient implementation for PEGs. So we're going to get into some of Python's grammar and read it and be able to understand exactly how Python determines what's valid and how its validity shapes the structure of Python code. But first, we're going to have to understand PEG a little more. So PEG is a set of rules. It's written on a file, so it's also a language. So PEG also has a grammar. So before we read Python's grammar, we are going to have to try and understand Python's grammar's grammar a little bit. This will be real quick, but after this, hopefully you'll be able to read all of Python's grammar and understand it. So the fundamental types for PEG are tokens, which we saw earlier with the tokenizing. They're always uppercase names, and they're just words that are found by the tokenizer. Keywords are quoted, and they can be actual keywords of the language, like import and class, or they could just be some string that is needed to be literally represented by for the parser. And finally, the kind of important one, rules. A rule is a name followed by a colon and definition. And the definition is any of these fundamental elements, possibly combined with operators of PEG. So rules can reference other rules, and they can even reference themselves. There's not really any ordering defined. Enforced here. So those are fundamental types. How can we combine them? Pretty much in these three simple ways. You either place one element one after another, in which case, in order to match that rule, you must match all of the elements in the order they're provided. If you want to match either or, you can use the bar, and you can then the rule match if either the first one or the second one or the third one or so on matches. And we can use parentheses to group our some or more elements, just like in Python code. We can repeat subsections of a rule. We can either make them entirely optional, so they can be present and the rule will pass, or they can just be absent and the rule will still pass. We can repeat elements 0 or more times or 1 or more times, much like a regular expression with star and plus. And we also have the option to repeat with a delimiter, which is easy to read if you think about it like the string.join method in Python, where you can have one without a delimiter, or you can have multiple, in which case between every one there must be this specified delimiter. And finally, there is some look ahead for PEG, positive and negative, again like regular expressions, and this thing called branch commit, where normally the parser will try all possible combinations, and so if the current rule you're on fails, it will just back up and check some other rule. This is always the case unless you've reached this tilde operator, in which case the grammar is saying you've come this far, you have to either commit or fail. So that was a lot, but that's everything you need to read all of Python's grammar. That's the complete syntax for PEG. So we're going to use that now to look at Python's grammar and see how it actually figured out what to do with our assignment statement. So we'll start our process of looking in Python's grammar with the assignment rule. Again, the PEG grammar states that we have a rule name, colon, and whatever its definition is. Here we have 4 branches, so any one of these could be an assignment match. It's neither of the first two, because if you take a moment to look at them, you'll see that they both deal with assignments that use annotations. And we didn't use annotations in our assignment. So we will in fact match the third branch, which is target equals an expression. And we don't have that trailing equals, which is asserted to not be there, and we don't have a type comment, but that's specified to be optional. So with this, we've built our first node. Note, when the AST is actually being built by Python, it's built from bottom up. So the leaf outermost nodes are the ones that are the successful termination of a grammar rule, and so they're built. And once you've reached the root node, you have a valid program, and so you're done. But we're entering the grammar from the top, so we'll build our tree from the top as well. So the assignment rule matched, but what it matched was some other rules. Our left-hand side of the equal sign was something called a star targets, which is another rule. So we go and look up that rule, and it's either of two options. It's either a single target or multiple with commas. So we will match that first one. That's just a single target, which is itself another rule. We check that. We're not using star assignment, so we jump to the second branch. We check out what this rule means. It branches differently depending on whether you're assigning to an attribute or a slice or something called an atom. So we're something called an atom. We look that up, and this has a couple options, but we match the first one, and you notice that in this branch there are no other rule names. So there's nothing else to recurse into in the grammar. We've hit sort of a terminal node. In fact, the name we found was up. So we found another node in our tree, and in fact we found our first leaf. We're assigning to up. That's all it is. It's pretty simple. We had to go through a couple rules to get there, but we pretty much ran right through the rules until we got to the name token. So now we'll back up to the assignment rule. We have a valid match for part of that branch we took. We still need to figure out what the value is that's being assigned. If you remember, that could have been either of two things. It could have been a yield expression or a star expression. The parser doesn't yet know this, but you and I know it's not a yield expression. So the parser would eventually figure that out by trying and failing to match that rule. Instead, we'll jump to star expressions. So this is, again, just kind of a rule around a single star expression. It says you can have one or more, but if there's multiple, there's rules on how they're composed. We only have one expression, so we go from here. Now we could go through all the rules from here to the leaf node, like we did with the targets, but it's a rather long journey. This is how many rules we have to go through to get to not even a leaf node, but to get to the next interesting rule. At each rule, we're taking kind of the default approach where nothing interesting is really happening. We're just descending further into the grammar. And the reason there's so many rules and that they're in a very specific order is largely to enforce operator precedence for Python. So it is important, and you can use what you know about PEG to go and read these rules if you'd like. But we're just going to jump from star expression all the way to primary, which is an interesting rule. This is primary. It has quite a few branches, and the first four of them are not only recursive, but they're left recursive of themselves. This is a thing that happens sometimes in PEG that makes it very powerful. So a primary can keep matching. You can keep having an infinite number of attributes, or you could throw slices in there. You can mix and match as much as you want, but eventually you have to find an atom or you'll never leave this rule. So what we match first is actually this middle branch where we're doing a call. Something is being called, maybe with arguments. And that's our next node, is that the value we're assigning is whatever comes back from this call. Now we don't yet know what we're calling or how we're calling it. We just know that it's a call. So we're back at the primary rule because although we matched once, we've actually recursed into ourselves. What is the thing that we're calling? It's requests.get. So we match this first branch. And get will be the name. We won't really figure that out until we get the other primary. So we recurse one more time into ourselves, and we eventually get to an atom rule. Now, atom can be a lot of things, but they're all very basic, usually ending the rule types. And for us, atom matches on name, the name requests. So we've matched a name token twice, but once in the atom rule and once in the primary rule. That's why they're going to end up at slightly different levels in the AST. Not super important. This is how Python knows which order it needs to look up those names. And now we know what we're calling, but we still haven't figured out what we're calling it with. And if we go back to our first match in primary, the thing we're calling could have an optional arguments. The arguments rule is pretty simple. It's just some bounds checking on a different rule called args. So we go check that. Args is a rule that has two branches because it's enforcing the ordering of quarks. You can either call something with quarks only, or you can call it with args and quarks. But if you do that, you must have quarks at the end. And you can have, say, multiple comma-separated arguments. We don't, but we do have a single one. It's, again, a starred expression. So we've been here before. And when we were here before, we kind of jumped all the way to primary because we went through some uninteresting things. We're again going to jump all the way to atom because we're not doing any bitwise operators or binary operators or anything like that. So args will eventually take us through this branch back to the atom rule. But this time we're not matching a name, we're matching strings. So there's a positive look ahead here for string, but there's actually one more rule to match, which is strings, because this is just because in Python you can actually have multiple strings back to back separated by only white space, and they're concatenated at compile time. So we didn't do that here, but that is legal in Python. And that's our final leaf node. We've finished, and at this point we'd recurse all the way back up to the assign rule, and we would have a valid match, and we would have a complete and runnable program. And that's kind of how the computer figured out what you meant by that statement. It used its grammar to take your statement and turn it into something that it could understand where the word boundaries are, what actions in terms of bytecode it needs to take for each of those words, and what order and precedence it needs to give each of them. And the next step would then be to just kind of decompose this tree back into some ones and zeros that it could execute. But that's trivially difficult after building this AST. That's it, and thank you for coming out to my talk.